So this experiment is been related to composite wall apparatus. So in this experiment we are going to determine the overall heat transfer coefficient of the composite wall. So in practice, heat transfer takes place through the composite walls, which is made up of several layers of different materials. The resistance to heat transfer is in each layer is different due to the thermal conductivity of the material and is analyzed by using thermal resistance concept. The concept of thermal resistance is been analogous to electrical resistance, is introduced to determine one-dimensional steady state heat flow through composite walls, cylinders or spheres. Thermal resistance depends on geometry and properties of material or medium. The rate of heat transfer through each wall is equal to the temperature difference divided by thermal resistance. So by the equation Q is equal to A into K and temperature difference T1 and T2 by L. So here the value of total thermal resistance R is being taken as equal to L by AK, where A is area of the wall normal to the direction of heat flow, L is the thickness of the wall, K is the thermal conductivity of the wall. For a composite wall, the thermal resistance are connected in series and total thermal resistance is equal to sum of the resistance of the individual layer. Thus, overall heat transfer coefficient of the composite wall is represented by the letter capital U, that is being equal to 1 by A into R total, where R total is the total thermal resistance and A is the cross section area of the composite wall. Now let us see the experimental setup. So here in this setup consists of 3 slabs of different materials of mild steel, halum and wood of different thickness clamped in the center using screw. Here you can see there are 3 layers of mild steel, halum and wood of different thickness clamped in the center using screw. A band heater is being provided at the bottom of the composite wall. So at the bottom you can see that there is a connection within a heater, and heat losses from the composite wall are minimized by providing in a thick insulation. So this is outer box what you have been seeing, that is in a thick insulation. The regulator is provided to vary the heat. Here we have been having a regulator, so where you can control the flow of electricity to the heater so that you can maintain a constant temperature, and when you maintain a constant temperature, constant heat is being generated. So those things we have been here, whatever the heat it is being generated, so we have been having this for control of flow rate of water. So what we have to do means, when you switch on the heater and you are going to vary the regulator for required heat input, then after steady state condition is being reached, you are going to record the temperature of the slabs. So you are going to that is being measured with help of thermocouples which are being placed over the surfaces of those composite walls. So here in this experiment you could not able to see those things on the surface. So here we have been having a temperature indicator where you are being able to sense the temperature at different values. So here in this tabular column we can see the temperature chart. So here the T1 we have been taking temperature at of the heater, and next we have been having a T2 that is in a mild steel, and T3 that is in a wood, T4 that is been copper, and T5 that is to open to the atmosphere, and T6 is at the water inlet, and T7 at the water outlet. Here all this are being measured with help of the thermocouples which are being placed, and we have been having a flow rate of the water, and we have been having a volumeter reading and ammeter reading, and we need to find out heat flow through the wall, that is the Q, and we need to find out what is a total resistance provided through experimental and the theoretical. From the observation we can see that diameter of the composite wall, here it is been given, that is D is equal to 150 mm, and thickness of the mild steel of the wall, that is been given of 10 mm, and thermal conductivity of the mild steel, here it is been given as a K1 55.4 watts per meter Kelvin, and thickness of the wood, that is L2, that is been of 10 mm, they have been taken. Thermal conductivity of the wood, that is 0.05, watts per meter Kelvin, and thickness of the copper L3 that is also been taken 10 mm, and thermal conductivity of the copper that is 386 watts per meters Kelvin. So here we are going to find out the cross section area of the composite wall. So you know the value of the diameter, you can get the area of the composite wall. The heat flow through the composite wall, we have been going to find out Q is equal to V into I, where V is the volumetric that is been taken from the reading and I is the ammeter reading that is been taken. Then afterwards, by applying the thermal resistance concept, heat flow through the composite wall can be written as Q is equal to change in temperature by R1, change in temperature by R2, change in temperature by R3, where T1 and is with respect to difference of temperature and thermal resistance across the mild steel wall, and T2 is the temperature difference and temperature resistance across the wood, and T3 is the temperature resistance across the copper. So we have been having T1 minus T2 and T2 minus T3 and T3 minus T4. From that you are going to get a temperature difference, and from that temperature difference, whatever the heat it is being passed to the composite wall, from that we could able to find out the R1 value. Once we could able to find out R1 value, we are being having observed thermal resistance value from the experiment, that is R1, R2 and R3. So we are going to add all those things. So you are going to get a total resistance. Then we are going to find out overall heat transfer coefficient value from the experimental, that is 1 by you know the area of the composite wall, and you know the resistance total. From this equation you are going to substitute it. This is the way you can find out from the experimental. Now you are going to find out theoretical overall heat transfer coefficient. So that is already they have been given. By using this equation we can find out heat transfer coefficient to the theoretical. So already we know the value of the L1, L2, L3, that is the thickness of the mild steel, wood and the copper. Then you know the thermal conductivity of each material. By substituting you are going to get the theoretical value of heat transfer coefficient. From this we can compare the theoretical value on experimental value.